Everybody, now we're going to go through some stoichiometry problems. What we're going to do is we're going to go through one example, but I'm going to show you a couple different ways that you could go about solving this problem. Now, whichever way you prefer is the one that you can use. I just want to show you both, just so you've been exposed to it in case you would see it in a homework problem or a test question. So this question asks, how many grams of CO2 will be produced when 11.6 grams of butane burns in oxygen? Now, before you do any calculations, again, find information in the problem. Read the question, break it down, and circle and underline a couple different things. The first thing you should do, underline any given pieces of information. Typically, given pieces of information has numbers. Well, this gives you 11.6 grams of butane. Now, some of you might know it, some of you might not. Butane is C4H10. So that's our given information. What it's asking us to find is grams of carbon dioxide. So we have a given piece of information, we have what we're trying to find. We're going to go through two different methods, dimensional analysis and BCA tables. Now, either method you choose, you have to start off the same way. The first thing you have to do is write your balanced equation. Once you have your balanced equation, convert your grams to moles. Okay, so those two steps are the exact same no matter which method you choose. So to start off with method 1, we're going to look at dimensional analysis. Now, this problem didn't give you the balanced equation. Just to save some time, I already wrote out the equation and I balanced it. Now, if you can't write and balance equations, watch some of the previous lectures before, look in your book for some practice, and go through that. This is a combustion reaction, so we have our hydrocarbon, which is butane, reacting with oxygen, producing CO2 and H2O. So this is balanced, and what I did under my balanced equation is I wrote our given, 11.6 grams, and I put a question mark with grams of CO2, right? Because that is from the problem. Then what I did in parentheses, because we're working with grams, I put the molar masses in parentheses. So I went through and I solved for the molar mass, and I found that C4H10 has a molar mass of 58.12 grams per mole. Carbon dioxide has a molar mass of 44.01 grams per mole. Now, these will be helpful. You're going to find as you start working through problems that you're going to know which molar masses you need to work with. If it helps you, just find the molar masses of all four, and then you'll be able to figure out what you need as you work through. So the first thing that we always have to do is convert our given to moles. So 11.6 grams of butane. Because grams are on the top, we need grams on the bottom of this conversion factor. So molar mass is always a certain number of grams for every 1 mole. So our grams are on the bottom, so that's where our number is, and then moles on the top. Typically, when you have grams, the only thing you can go to is moles. So we have grams to moles. Notice these units cancel. Now we have moles of butane. We don't want moles of butane. We need to get to carbon dioxide. However, to get from one substance to another, you have to use your balanced equation. Coefficients tell you number of moles. So I have moles of butane. I'm going to use my coefficients. By looking at this balanced equation, I see for every 2 moles of butane that I burn, I produce 8 moles of carbon dioxide. So I'm going to put those coefficients in here. Now, my moles of butane cancel, and I'm at moles of carbon dioxide. However, the problem doesn't ask me for moles of CO2, it asks me for grams. So I have to take it a step further, cancel out my moles, and go to grams. And then we solve this, multiply across the top, divide by what's on the bottom, and we get 35.135 grams of CO2. However, our given is 3 significant figures, so my answer needs to be 3 significant figures, which means I'm going to have 35.1, but because this 3 is less than 5, this 1 is going to stay a 1 and it's not going to round. So we get 35.1 grams of CO2. Now, just to summarize what we did in this, we wrote and balanced our equation. You convert your given to moles, use the mole ratio to go from one substance to another, and then convert back to the desired unit. So this is using dimensional analysis to solve the stoichiometry problem. Typically, this is going to be the quickest way to solve a problem, but I want to show you the second method, which involves using what are called BCA tables. Now, in the lecture, I went through what a BCA table stands for, before, change, and after. But the reason I want to show you this is because once we get into limiting reactants, this actually might be more helpful in determining the limiting reactant. So I set up the BCA table, and I have our written and our balanced chemical equation. Now notice, just like the last one, I did grams and I found the molar mass. Okay, so we have our given, we have our molar masses of everything. And what I did is I crossed out oxygen and water because the problem does not mention O2 or H2O anywhere. So what we have is just our butane and our carbon dioxide. Now this B stands for before. So before the reaction, how much do we have? Remember, the only thing you can put in these BCA tables is moles. So what we have to do first, just like when we did it using dimensional analysis, is convert our given to moles. So I did that down here already. 11.6 grams, go grams to moles, we get 0.19959 moles. So I will put that in here. Okay, that is our initial number of moles of butane. Now, before the reaction even starts, do we have any carbon dioxide? Do we have any products before the reaction takes place? No. So I'm going to put a 0 here, right? We don't have any moles of CO2. Now, this change row is very, very important. What we do is we use up our reactants and we form products. So in this change column, we're using up our reactants and we're forming products. What we have to look at here is our mole ratio. This is where our coefficients come into play. For every 2 moles of butane, we form 8 moles of carbon dioxide. However, do we have 2 moles of butane? No. We have 0.19959 moles. So what we have to do here is look at the ratio. Okay, what we can say is this ratio, we need 4 times as much CO2. Right? If we simplify that, for every 1 mole of butane, we make 4 moles of CO2. So what I did down here is I used the mole ratio. I said if we have 0.19959 moles of butane, when we use 2 moles, we make 8 moles of CO2. Okay? And I found my moles of CO2 that we would make. Now, another way you could do that is say, well, I'm going to use up all of this. Right, because it's our only reactant, we're assuming the reaction goes to completion. So after I have 0. Now, I make 4 times as much, right? An 8-to-2 ratio is a 4-to-1. I make 4 times as much CO2. That's going to give us the same thing as down here. So when I multiply this by 4, I get 0.79836 moles of CO2. Right? Notice, again, that's the same thing down here. So, here now I have my moles of CO2. Does the problem ask for moles of CO2? No, it asks for grams. So, what we have to do, and I did it down here at the very bottom, is we have to take our moles of CO2 and go to grams using the molar mass. When we do that, we get 35.1 grams of CO2. Notice that's the exact same answer that we got using dimensional analysis. You will get the same answer. It just depends on, do you want to just do, the full arithmetic with using the dimensional analysis, or does it help you to visualize the material? Again, up to you. I just wanted to show you both methods.